Greetings, welcome to the talk, Python templates for neural image classification and spectral audio processing, part 1, Lightning Hydra Template Extended. So what is all this? Well, the Lightning Hydra template is something a lot of people use to get started with their machine learning projects in PyTorch. And it has a little example for image processing and image classification. So I got inspired by that and decided to add on to it and just learn a lot about image processing that way, because ultimately I want to do spectrum processing. I want to do spectrograms to parameters of various types. So, so this is the extended template. Started with a fork, and then what it does natively is gives you your Hydra support, gives you PyTorch, the Lightning wrappers for your modules to help make them a little more easy to train and to work with. So there's just a lot of conveniences there. It's very well used. The chatbots know it really well. That really is a huge advantage I didn't expect. They really know how to get around in it and never get confused, unlike my other code bases. So the LHTE Lightning Hydra template comes with a multi-layer perceptron trained on MNIST, just a very simple little example just to show you how everything works. And it trains up and it gets state-of-the-art results, and it's really exciting. It's just a little network that works really well on handwritten digits. It's a standard data set for that. So what's happening in the extended version, LHTE, is we're adding CNNs, Vision Transformer, ConvNeXt, which is sort of the CNN answer to Vision Transformer or to transformers in general. It incorporates a lot of the ideas and does really well. And then EfficientNet, which is really good for small systems, like if you're going for a phone or something like that. And there's also more dataset support. So in addition to MNIST, we have SciFar 10 and SciFar 100, and I have some previews about that. And then a new one I'm calling VIMH. It's like hyperbolic sine is pronounced cinch. So this is the variable image multi-head format, and it's basically a generalization of SciFar 100. And so you can have up to 65,000 by 65,000 images, and each image can have up to 65,000 channels. So that's RGB and whatever else. But in my way of thinking, it's, alternate spectral representations. So you can put alternate time frequency resolutions. In those planes, you can do modulation spectra, instantaneous frequency, instantaneous delay. There's a lot of things to try there that might help the network learn a little more efficiently. And so it's also got multi-head support. So that means there's a shared network, and then it splits out into separate classification heads. And those are 8-bit labels and 8-bit values. So up to 256 heads and 256 logits coming out of each one. And so where I'm heading with this is synthesis parameters. So spectrogram to synthesis parameters. And so these limits have not been binding and probably will not be. I'm limited to 256 parameters, and I'm at half that right now in physical modeling. And then each one has, up to 256 actual settings. So the knob can only have 256 clicks, and that's the number of logits in the classification case. But I also support regression, just plain regression, numerical interpretation of the knob. So comparing those, actually right now regression is winning. So I might not even use classification in the end, but other people, things I read about, other people are getting better results with classification over regression. And there's a bit of a story there. So anyway, everything has data loader support, and the model architectures know how to read the various data sets. And so there's an experiments directory, which has a lot of, nicely frozen examples, including benchmark replications. And so, for example, SciFar data sets are very well known. I mean, there've been a lot of competitions. It's like 15 years old or something. It is, in the 2000s that they were really working on this stuff, and that's why it runs really fast right now. And You get small networks by today's standards, but the great thing about being able to replicate those benchmarks is that you know that you don't have a bug. So you ingest these architectures, which I did using Claude. I found the best code I can find on the web, and then I told Claude to integrate it into this template environment, into the Lightning environment, and it did it. And you need to be able to test it, right? And so if you can replicate these benchmarks, you're doing quite well. You trust your integration pretty well. All right, and I like Makefile. So there's 80 make targets for testing and training experiments. So you never have to type very much. It's also actually, I find, very convenient for sending a chatbot off to go debug. You just say, please debug make T, and it'll go run your tests and find the bug and reproduce it and fix it. So first, a little bit on the original Lightning Hydra template. It's free on the web, of course, and it's a template. And so it's a skeleton with a source directory, a configuration, that's Hydra configuration, and a test directory. That's your basic PyTest stuff. And there's also under configs, there's your experiments directory, and that's an important one. And and chatbots really love it. They've seen a lot of this, and they know how to get around in it. And that was an unexpected dividend of being in this framework. And so the Hydra workflow is really nice. You can override, so you can run Python on your train script, and then override the there's a default case in there, and then you can override the default, say, I want the GPU, I want to change the bat size. And so this is a config file with a data, struct, I think of it, and then it has a field, which is batch size, and you can just override all these things from the command line. Very convenient. And the chatbots really know how to do with this. So they'll run experiments for you. They'll just make lines like this in order to try things out. So they're very, very fluid with it. And so there's a lot of possibilities here. And so let's see. So the original LHT just had NSMT, and so now we have more, and that's the basic idea. So if you want more image processing stuff, this is a good place to start. And as I said, I'm using it for spectrogram signal processing of various kinds. And so another thing is that all the extensions are backward compatible, so you can still run the original MNIST experiment, and that's in there. So you shouldn't have any problems if you've been using that template before. You should be able to move to this without breaking anything. So as I mentioned, the data sets have now been extended to CIFAR and VIMH. And so CIFAR 10 is this little 32 by 32 RGB. So MNIST is 28 by 28 grayscale. And so you only have 10 classes here. And so, as I said, if you reference it, then you'll automatically download it. There's 50,000 training, 10,000 tests. And so, so there are these, you can run these examples and get CNN 85 to 92% accuracy, Vision Transformer, ConvNeXt. So this tells you what to expect when you run the benchmarks. And here's how you might run a benchmark, using the Makefile. You can, I have all these abbreviations. So let me just show you quickly how I run these things. So, so you can say make help, and you can just abbreviate that H, and I'm in the wrong directory. Make H, and there it is. There's all the stuff. And if you just want to know, for example, I have this little thing, make help grep, and so I can say make help grep. What do we want to do? Everything to do with CIFAR. And so there's all so you can pick out one of the benchmarks there. And of course, there's a README that will get you started. And I like to view that in Cursor. It's got a nice Markdown previewer, from the VS Code world. So that's just kind of how you get it up and running. You just explore the make targets and see what they're doing, and get your chatbot to explain everything to you. So there is an example of some of the images. All 10 classes are right there, in fact. And see, within each class, you'll have, a large number, I guess 5,000 roughly. So that's kind of the workflow and how it looks. And and you can verify it and feel pretty confident about it. And then we also have SciFar 100, and so that's now got 10 categories. I'm sorry, 20 categories, and they're considered coarse super classes, and then 100 fine classes. And so I'm using that basic idea to map it to the synth matching problem, where I have, in my case, would be like 20 synthesis parameters with 100 settings on each knob, that kind of thing. So I want to kind of, leverage this long-standing image classification research to, see if it can help me with my problem. And I'm, comparing a lot of things, comparing vision transformer to CNN and seeing what works best and what's lean and mean and runs fast. It'd be nice if it runs in real time, right? And so, so here are some of the benchmarks, and so I've got multi-head as well, and so here's how you would run, for example, the SciFar benchmark, SciFar 100, using CNN. And so you can also spell that out in more details, and you should see somewhere in this range of accuracy. And you can look at it in TensorBoard and see if it's really done. I might not run quite long enough to get you that high, but you should get close. So that's the basic idea. Oh, and this one will run all of the benchmarks. So the entire suite of benchmarks make SciFar benchmark suite, SciFar 100. So that's how you can run all these things and test them out. Okay, so that's SciFar 10, SciFar 100, and then the other data set we have is VIMH, variable image multi-head. And so here's how I'm using it, not in this project. This is from another project that's in part 2, my next talk, I'll say. And so the images are spectrograms. Here's the input spectrogram. Here's synthesis from the parameters in the data set. This is predicted. So the neural net came up with these parameters and synthesized this. And this is actually an overlay of the true waveform and the original waveform. And this is a sawtooth through a wah pedal. So there's a decay time, and there's a wah position, and it just nailed it. So it's just really working. This is my, version of the MNIST MLP that came with LHTE. So LHTE extends that, and then in my next project, I'll have Neural Spectral Modeling Template. Okay, so these are the things I said before, the size of it, flexible labels, and it's self-describing. So the data set tells the architectures what's there, and so everything adjusts to the data. So if you want to change your spectral dimensions, you can. All these channels have to be stacked up at the same, height times width. And so so they're all the same in that sense. So that's kind of the architectural prior, so to speak. And so I just showed you how you can do make help, and you can grep for something. And so yeah, we can just let's do a make help grep for VIMH, and you can see what the targets are. So you see just there's a number of them here. You can also do diagrams. So let's look for diagrams, and you'll see a number of things you can do. So let's make TDA, that's text diagrams for all architectures. And so it makes these nice text diagrams. They're really cool because you can see what you have, what you're using. There's two formulas. There's kind of a Lisp-like, I guess that's Python syntax for the whole thing. And then you have these nice block diagrams. And I think that's good enough, All right, so those are the new data sets, the new architecture, and now the new architecture. So CNN, this is classic stuff. Don't need to spend a lot of time on this. But this is an automatically generated diagram from Claude. It just went through. I gave it that text diagram, actually, and it did me a nice little figure here. It's something. And so here are the kinds of things you have. Just 2 convolutional neural network layers. And, this is classic CNN stuff. So for SciFar 10, you should see 85 to 92%, SciFar 100, 55 to 70. And so the experiments that are here have, a small 8K neural net, 68K and 421K. And we saw 1.2 million for, the next project. So these are all down in the million or less range, and they do very well. And I mean, and the reason you can get away with something this small is because, it's only 32 by 32 by 3. It's a very, very small input. And, but of course, the classification challenge is quite difficult. So in spectrogram recognition, it's not so bad, and in a well-conditioned spectrogram can do well at 32 by 32. I'm getting good results at that size. So as I said, we added multi-head classification and regression. So these are the architecture config files, and it's not as bad. So we got all the CIFAR 10, all the CIFAR 100, all the MNIST, and we have 3 sizes, usually 64, 128, and 210. So, you have just kind of a smattering. Here are your vision transformers, EfficientNet, ConvNeXt. And so these are just the ones that I developed because I wanted to try them out, right? And why not just leave them around? And so they're all there. And then, of course, the LHTE has exactly this one, just example.yaml. And that got me off and running. And so, I don't claim all these are well tuned, but some of them are. Some of them are tuned up to replicate benchmarks. And so they're gonna give you really good results for those benchmarks. But you'll have to, have your favorite chatbot tune up yours the way you want it. Here's ConvNeXt, and you can read the paper. It's the response to vision transformer in the CNN world. Here's EfficientNet, I mentioned. Here's vision transformer. And I've only got a minute, so I'm just going to breeze past these. It's all super standard stuff, but it's good state-of-the-art stuff. These things are not obsolete. Transformer does not make any of this stuff go away. Well, Transformer is used in vision transformer, but CNN still when the translation invariance is a reasonable assumption when you can get by with that. And here's a diagram of the multi-head classification. You have shared features and you break it out. And these are either classification heads or regression heads. You have both. And so there's that. So then finally, there's this just kind of a little bit about the workflow here. You got the experiments. I showed you some of the architecture files and how to get around using make a lot. Don't type too much. And then yeah, we covered that pretty well. Here are all the experiments at the moment, and it's got some benchmarks and some regression stuff. So that's about it. And the next steps are, merge PRs, and every time a new chatbot comes out, I'm going to have it go through everything, see if it can suggest improvements, and that's about it. And here's a summary of all the. So this is the original Lightning Hydra template, and here is the extended version. And here's what I'm going to talk about next, and that is the Neural Spectral Modeling Template. It's just a fork of this, And here's my homepage. I'll have links to everything there. The video that comes out from ADC and so on. All right, that's it. And I'm only 1 minute over, so I'll go on to the next talk.